Great, it's recording now. Today we are going to talk about section 2.3, the limits laws. Okay, so but before we go into the limits laws, which are a set of formulas, I gotta tell you about these two very, very basic results. How to compute the limit of the identity function at any input value, and how to compute the limit of the constant function at any input value. Let's start with this one first. The limit of the function x as x approaches k. You know that when you graph the identity function y equal x or f of x equal x, you get this diagonal line, right? 1 gets paired with 1, 2 with 2, -1 with -1, -2 with -2, diagonal line. But now, since we're doing calculus, we're going to figure out what should be the limit of this identity function as x approaches, let's say, some real number k. Suppose the real number k is here. Suppose it's here. Let me make it bigger. Is here, okay? Okay. Could be positive, negative. I'm just taking a positive real number k. Now go up to the function, the identity function. Since it is the identity function, is going to pair up k with itself, with k, right? With k. Now, in order to figure out this limit, remember, since limits are all about what happened with the output values when you approach an input value from the left and from the right, I'm going to start by approaching from the left, okay? If I approach k from the left this way, the corresponding output values, they go up to k, right? K. And similarly, if I approach k from the right, and I look at what happens with the output values, they come down to k as well, right? There is convergence, right? From the left, I'm going to k, from the right, I'm going to k. So I have the right to say that the limit of the identity function x as x approaches k is just k, is just k. So from now on, when we encounter this function, we're taking limits, we just sort of plug this into there, into the function k, right? K. Very good. Next basic result is this. What should be the limit of the constant function f of x equals c, where c is some real number, as x approaches some real number k? Again, if you graph the constant function, that is just a horizontal line, right? If your value of c is positive, the horizontal line will be above the x-axis. If it is negative, it will be below the x-axis, right? But now we're trying to figure out the limit. So if we consider k to be here, and we approach this k first from the left, the corresponding output values, look, since the constant function k is paired up with this real number c, it's a constant function, they all approach c, right, output wise. And similarly, if we approach k from the right, if you take a look at the output values up here, they approach to this constant real number c. So conclusion, from the left, you're going to see, from the right, you're going to see output y. So the limit of the constant function c as x approaches k should be a c, right? It's itself. The constant function never changes. Even when you take limits, it stays the same, c, right? For the identity function, you plug this into here, k, right? Very good, guys. So these two results you should memorize. We're going to use them so much that if you know them by heart, it will be good. Okay, so now, having gone over this basic, let's just check our knowledge here via these 4 examples. Suppose I have to take this limit of the identity function x as x approaches 5. What will be that? Well, we said that since the identity function pairs the input value with itself, we showed before that this is just itself, 5, right? So this should be 5. And I kind of want you to kind of develop this idea of plugging these values into root. I'm sort of plugging this number 5 into the identity function, I get 5, right? Good. Now, what about this other function? The limit of the constant function 7, as x approaches -3. Remember, the constant function never changes its value, not even when you take limits. So the limit of the constant function 7 as x approaches -3 should be just 7, right? 7. Then I will give you some exercise more words you will have a chance to practice. But now, can anyone tell me what should be the answer for number 3? The limit of the function a as a approaches 1/2. You can write it on the chat. You can say it verbally if you figure this out. Someone wrote it on the chat. I see you guys, you're sharp. Deep. Excellent. Very good, right? Yeah, remember, try to develop this idea. That limits can be found somehow by plugging values into. Look, this is the identity function. So just plug it into here, 1/2, right? Identity function is well behaved, so you can do this. Now, what about this, number 4? The limit of the constant function pi as x approaches 2. Anyone could tell me what should be this limit? Chat. Man, great, excellent. Very good, right? The constant function never changes its value, not even when you take limits. It stays the same. Pi, right? Yeah, very good, guys. So when you encounter these scenarios, you know what to do, right? Excellent. All right, moving on. Now we are sort of ready to talk about the limits laws. Mathematicians studied these limits, and they found out that there are several limits laws that these limits obey, these limits follow. First one is called the sum law. It says that if you take the limit of the sum of two functions, that is equal to the sum of the limits of the functions. In other words, to put it simple, this is saying that limits behave very nicely over sums. Why you say very nicely over sums, Professor? Well, in the sense that you can distribute the limit over sums this way, right? Limit of f plus g equal limit of f plus limit of g. Great. Also, mathematicians discovered that limits behave very nicely over differences. In what sense, Professor? Well, you can also distribute the limit over the difference of two functions. Limit of f of x minus g of x is equal to limit of f of x minus limit of g of x, right? Very natural formulas for limits. Then also mathematicians figure out that if you are dealing with a function that is multiplied by some constant c, some real number here, then you should allow yourself to take this constant outside of the limit, right? And focus on taking just this limit of the function. So when you see a constant multiplying a function, feel free to take the constant out and then multiply that constant by the limit, okay? It's called the constant multiple law. Great. Continue here. Let's continue here with the product law. What's the product law? Mathematicians discovered that limits behave also nicely over products, multiplications of functions, right? That's what the word product means. In what sense, Professor, they behave nicely over products? Well, in the sense that you can distribute your limit over products. The limit of the multiplication of two functions is equal to the multiplication of the limits of the function, right? You can distribute your limit over multiplication and go from this scenario to this scenario. Great. Also, mathematicians showed that limits can be distributed over quotients, or divisions of polynomials or functions in general, right? So the limit of f of x divided by g of x should be equal to this limit of f of x on the numerator over limit of g of x on the denominator, right? The limit of a quotient is the quotient of the limits. Okay, great. Now, with these laws, probably we should go over some exercises. But before we do that, let's talk about these two final laws here so we can complete it and go over nice exercises. the power law says that if you're taking the limit of a function raised to some exponent n, then you are allowed to put the function together with the limit inside the power. In other words, you are allowed to put this limit inside this power, and this should be equal to the limit of f of x raised to some power n, right? Similarly for radicals. Radicals can be placed inside, or limits can be placed inside these radicals. So limit of n root of f of x equal to the n root of the limit of f of x, okay? This is the power law and the rule law. All right, so with all these laws, we can then compute limits algebraically, right? Look, for example, take a look at this example 1. Limit of 4x plus 2 as x approaches -3. I'm gonna do this first, following all our laws, right? And then we kind of will figure out a shortcut for this, okay? First, if we apply the laws that we just stated, one of the laws, the sum law, says that we can distribute our limit over sums, right? So we can get this for x plus the limit of the constant function 2 as x approaches -3, right? Good. Next, I have what is called the constant multiple law, right? That says that if I have a multiple or a constant multiplying a function, this number 4 is multiplying the identity function, right? I should be able to take that constant outside of the function, outside of the limit, better said, right? And focus on taking this limit, right? Great. But now, let's now figure out what is this guy, what is this guy. First, what should be this guy? Limit of x, the identity function, as x approaches -3. Anybody could tell us in the chat or verbally, what is this limit? Someone wrote to the students. Deep, very good. Robert also, very good. I see guys, you're sharp following. Yeah, this is the identity function, right? Remember, just plug it into there, -3 here, right? For the identity function. And this one now, the limit of a constant function. What is the limit of this constant function? 2 as x approaches -3. Hint, the constant function never changes, right? Not even when you take limits. Man, very good, excellent. Excellent, right? It's a constant function, so it shouldn't change. This is 2. We talk about this. These are the 2 basic results, right? Now 4 times -3 is -12, right? Multiplication first, remember? Plus 2. And finally, -12 plus 2 is just -10. And we are done, right? This is the limit, -10 of this function as x approaches -3. Great. In example 2, they are asking us to do the same, but this now is a polynomial function, right? So let's do it again, following first all the rules, and then kind of let's come up with an efficient way to do this. So if you follow the laws that we just stated, what you have to do there? Well, first, allow me to distribute my limit over the sum, right? Over the sum and the differences of these terms. There's a difference, there's a sum here. So we know that limits behave very nicely over sums, over differences. So I should be able to distribute my limit over, right? This should be equal to this, right? Limit as x approaches 1 of twice x plus the limit of this constant function 4 as x approaches 1. Next, I notice that there's a constant number 3 here multiplying this cubic function, right, x cubed. So there is a law, a constant multiple law that says that I can take this constant outside of the limit, right, and focus. Focus on this. Man, you raise your hand. Do you have a question? Go ahead.
Yes, Professor. I just wanted to ask, why did the square become a cube?
The square because thank you. This is a square. This is just a square. I didn't see it well, so thank you so much, man. Okay. Yeah, very good, guys. That you're saying, yeah. Anything, something doesn't make sense immediately, guys, say it loud, because mathematics, we don't have room for ambiguity. Great, excellent. Now we're good, right? We're 2. Now, 2 is a constant, comes out of the limit, and we focus on taking this limit, identity function there. And this is the limit of a constant function. It's a constant function as x approaches 1. Now, guys, look at this part. Remember, we have this so-called power law, right? That says that you can put the limit inside, right? You can put the limit inside, and square this limit, right? Square this limit. Yes, the power law when you have to deal with exponents. Then let's copy the rest. Okay, now I'm gonna ask you this question, guys. What should be this limit here? Limit of the identity function x as x approaches 1. Let's see this guy, right? What should be this? I see in the chat. Excellent, right? Robert, Manu, excellent. This is just 1, right? 1. Minus 3 times what? Again, what's this guy? We just saw that this guy is 1, right? 1. Excellent. And what is the last one here? The limit of this constant function as x approaches 1. Manu, excellent. Robert, also great, right? Yeah, this limit is just 4 because we're dealing with a constant function that never changes, right? Great, guys. All right. So now I wanted to capture the following. It is good to capture or catch patterns, right? This I want you to remember. Okay, we're gonna do this first. We're gonna compute this, and then I will go back there. Look, this will be 1 squared 1 times 3, 3. 3 minus 3, 0, plus 4, 4, right? 4 is, yeah, so this is a, let's forget it. This is 2, sorry, I mixed up this is 2. Yeah, so let's be careful here. 2 here, right? This was a 2. 2. Okay, let's do it again. Look, 1 times 3, 3. 3 minus 2, 1. 1 plus 4, 5, right? 5 is a 5. This is the answer, right? 5. We follow formally all our rules, our laws, right? We ended up with 5. But look at this parenthesis here. This parenthesis, and look at this guy, 1, 1. Try to make the connection here. Look at 1 here, 1, 1. And this is just the structure of this polynomial, right? So when I look at this back, I kind of say to myself, didn't I just evaluate this polynomial at x equal 1, right? Didn't I do this? Answer yes, right? So from now on, guys, when you take the limits of polynomial functions, it is enough to just plug this value into here, okay? That will be for polynomial functions because they are super nice functions in calculus. I'm gonna write it as a property here. They allow this so-called direct evaluation. So property here, if f of x is a polynomial function, okay? Then the limit of f of x as x approaches k is just f evaluated at k. So basically, you just plug the value into there to get your limit, right? To get your limit. So let's write this out nicely here, f of k, right? F of k, evaluation. This is what the mathematicians call a direct evaluation. Direct evaluation, I'm gonna write it here next. Direct evaluation, also called direct substitution. Direct substitution, direct evaluation. Okay. All right, so for polynomial functions from now on, we just have to do direct evaluation. So before moving forward, guys, before going over the case of taking the limit of the rational function, probably you should practice here first. This direct evaluation, I want it to be clear. Yeah, but perhaps maybe it's just better to do this once and for all. All right, so I know that in order to take the limit of a polynomial, it is enough to do a direct evaluation, right? So what if they ask me to take the limit then of this function, the quotient of two polynomials? Well, following the quotient rule, I can say that this is going to be equal to the limit as x approaches 3 of twice x squared minus 3x plus 1, right, the numerator. And here, the limit of 5x plus 4 as x approaches 3, right? As x approaches 3. But now, we just said that in order to take the limit of a polynomial, it is enough to plug the value into, right? Yeah, great. So we do that, and we're gonna get 2 times 3 squared minus 3 times 3 plus 1 over here. This is a polynomial 2, right? Polynomial degree 1 plus 4. And basically, work this out, and we should be done, right? Now, this is 9 times 2, 18. 18 minus 9 is 9, plus 1, 10, right? 10 here. Here, 5 times 3, 15, plus 4 is just 19. 19. Yeah, great, right? Very good, that's it. Now, so the moral of this story is, right, this first method called direct evaluation, as long as it works, as long as doesn't lead you to something undefined, should be used, right, first. And if you get a meaningful real number, then you are done. Then you are done, right? You may say, what if we don't get a meaningful real number, Professor? Well, I will give you other techniques, alternatives to overcome that situation. Okay, but for now, first, always try direct evaluation. Okay, guys, time for you to practice, okay? Time for you to practice. Remember, practice makes the master. Let's do this first. Can you try this one? I want to write it bigger for you here. Limit of this function x squared plus 5x minus 2 as x approaches 1. Work this out and recall the fact, right? Remember, for polynomial functions, since they are well behaved in calculus, it is enough to do a direct evaluation. I see. Deep already figured this out. Very good, very good. Yeah, excellent, excellent, right? Yeah, when we're dealing with polynomial functions, a direct substitution will suffice. Miguel also, very good guy. Very good, excellent, excellent. Yep. So if you are given the task of taking the limit of a polynomial function, it shouldn't be a problem because it's all about plugging the values into, right? This guy into that. This is 1, this is 5, 1 plus 5, 6, minus 2, 4. And this is it. We got a meaningful number, we are done. There we go. Now I gotta warn you about this situation, right? What if when we try to substitute, you get something undefined? For example, here, look, 8 substituted into here will give us 64, 64 minus 64, 0, 8 minus 8, 0, 0 over 0. Undefined, right? What to do in those cases? So let me go back to the lecture and show you an example, and we'll come back to this, okay? So here in our notes, it says, what if direct evaluation does not work? Does not work. What do you mean does not work, Professor? Well, I mean this. If you plug this into here, you're going to get 2 squared minus 12 times 2 plus 20 over 2 minus 2, right? But this is 4 minus 24 minus 20 plus 20 is 0, right? 0. 0 on the numerator, 2 minus 2, 0 on the denominator. This is what mathematicians call undefined. Undefined. But remember, the limits do not deal necessarily what happens right at x equal 2, right? At x equal 2, this function is showing some undefined result, right? But since limits are concerned about what happens on the neighborhood of this number 2 on the left, on the right, then don't take this as your answer. Instead, try this, factor and simplify. So by factoring and simplifying, we may overcome this undefined situation. You will see. So if we factor and simplify this guy turns out is just the following. I will show you. Limit as x approaches 2 of factoring, or here factor, this is already factor x minus 2, but here on the top, I can factor this quadratic trinomial as this. I gotta look for two numbers whose multiplication is 20, whose sum is negative 12. After some trial and error, you will figure out that these numbers are 10 and 2. But since you want the sum to be negative, this must be negative, this must be negative, right? But now, when you look back here, you notice that these two factors are the same, right? So this means that we can eliminate them, right? Eliminate them. And this is telling us that this complicated function that they gave us here is just this, It's simple, it's just this, x minus 10, right? Now, this function is better behaved. Why you say that, Professor, that this function is better behaved than this? Well, because this one will allow you to do the direct substitution now. You will see that now that you do direct substitution, you will no longer get yourself in trouble, like in here, right? 0 over 0. It's no longer that. It's 2 minus 10 minus 8, right? Minus 8. And this should be the value of your limit, right? Minus 8. Okay. So first technique to overcome this undefined situation when you do direct evaluation is to use factorization and eliminate that factor that was causing this undefined situation, right? Yeah. And then you plug the value into, you try direct substitution again, and we should be fine. Now going back then now to this another example here. Yeah, but I'd rather you try this first. Can you try this? Number 2. And then we will go back to another more challenging exercise. Can you try this? Limit of x squared minus 64 over x minus 8 as x approaches 8. That's right. Hint, if you try direct evaluation, as we mentioned right before, unfortunately 64 minus 0 and this 0, so it doesn't work. So now try factorization, right? So the hint will be factor and simplify. Yeah, go ahead. Yeah, give it a shot. It's not that difficult. And also probably you should recall this result from algebra. A squared minus b squared equal a minus b times a plus b, right? It's called factoring the difference of two squares. So x squared minus 64 as a hint is the same as this, right? So use this as your factorization and then simplify. And then plug the value into again. Yeah, and then eventually I will tell you what to do if some radical appears, some radicals appear there, right? Yeah, I will tell you what to do. I see activity on the chat room, which is good. Yeah, give it a shot, guys. You don't have to be right all the time. Manur. I see. Let me check. Yeah, excellent, excellent. Yeah, you made my day. Excellent, excellent. Also, Karen, good job there. Great, excellent, guys. Right? If we try direct substitution, doesn't work. Give us undefined, right? But don't go for this, right? Not yet. Instead, try to overcome this situation by using factorization and simplifying, right? So this guy factors as x minus 8 times x plus 8, right? The numerator. The denominator is x minus 8. So we notice that x minus 8 here and x minus 8 here on the bottom cancel. They both cancel. And then we are left with this simpler function, right? Turns out this rational function was indeed this simple function. Limit as x approaches 8 of x plus 8. Now this function is better behaved because this allows the direct evaluation, right? 8 plus 8, and that is 16. Good, excellent, excellent, guys. That's it, right? Very good, very good. All right, there's another one here. This one is very similar to the example that I did, so probably we should try this, but let me show you another example, like this form, for you to see what to do when there are two different types of factorization that you must apply. This one is good. Example 2, suppose they say compute this limit, the limit of this rational function x minus 3 over x squared minus 9 as x approaches 3. What is this equal to? First thing, we try a direct evaluation, right? And I would advise you to try that first always, right? Because what if it works? If it works, we are done, right? We're done. If it doesn't work, we have techniques to overcome that. If we do direct evaluation, however, 3 minus 3 is 0. 3 squared is 9. 9 minus 9 is 0, right? 0. Undefined. All right. So then it means that we have to factor and simplify, right? And simplify and try again. Factor and simplify. If you do that, this becomes limit as x approaches 3 of x minus 3 on the numerator. On the denominator, since this 9 is equal to 3 squared, we use this so-called difference of squares method to factor this guy, right? And end up with x minus 3 times x plus 3. But this shows that I can simplify this factor, right? This factor, look, this factor x minus 3 here, right? X minus 3 here, x minus 3 here. These two, they get simplified. But be careful, guys, when you simplify this type of expressions. Look, apparently nothing is left on the numerator, right? But there is always this invisible one up front, right? And that should be left there, should be left there. So this, when simplified, will end up being this 1 on the numerator, right? Because of this invisible one, and x plus 3 on the denominator. We got another rational function, right? Looks like a fraction of polynomials. But however, I would say again, this function compared with this function is better behaved, better behaved. Why you say that, Professor, better behaved? Well, because this function allows me to do the direct evaluation, which is this, without giving me trouble, without giving me 0 over 0. So that's the goodness of this new version of the function. So 1 over 6 should be the answer. When you show the answer in this form, 1/6. This is what mathematicians call exact form, exact form, okay? All right, so now let me talk about something here, okay? When you're doing, let's say, your homework and you're using your calculator, suppose you use your calculator to compute something like this. Suppose the computation is not simple and you use the calculator, right? 1/3 + 3. Our decimal scientific calculator is going to show this 0.166666, the decimal representation of this first by default, right? But if you want to catch the exact form, not a problem, just click here, convert it to a fraction, 1/6, right? And it will appear there. So if in the homework, it is required that you have to post the exact form of the answer, just switch it, right? From decimal form to fractional exact form, okay? Don't get stuck, guys. Yes, always use your tools, go through the exercise. All right, great. So now, remember, right, when you eliminate something on the numerator, there is always a 1 left there. All right, so now let's go back to our worksheet and let's see if we can do more here. I saw a nice exercise here. I had this one, number 5. Can you try this? Try guys. Hint, factor, numerator, and denominator. I'm going to write this as a hint, okay? Hint, factor, numerator, and denominator. Both, right? And simplify. And simplify. I see. And the last hint is write it in exact form, your answer, right? Deep. You got it? Very good, very good. Yep. Yeah, try, guys. And again, if you don't find your answer, if you're using a calculator and you want the fractional form, I show you how you can get it from our decimal scientific calculator, right? Yeah, you can go back and forth from decimal form to fractional form, which mathematicians call exact form. Of course, once the fraction is simplified, right? More answers. Yeah, which is good. Miguel, excellent, excellent. Good job there. Yeah, very good, very good. Yeah, you should master all these worksheets, guys. It's a very, very a strong base for your preparation toward exams. Okay, so make sure that you are crystal clear with all these forms. All right, great. And also it's going to help you in the homework, right? Yeah. All right, so let's do it together, right? So we got to deal with the limit as x approaches 5 of this rational function, x squared minus 25 over x squared minus 7x plus 10, right? And first thing we do, we try direct evaluation, right? Professor, why you try direct evaluation first? Well, what if it works? If it works, then it means that I'm done, right? I don't have to continue. So let's try, just in case, this direct evaluation. 5 squared minus 7 times 5 plus 10. But now, unfortunately, 5 squared 25 minus 25 is 0. And here 25, 5 squared minus 7 times 5, 35 minus 10 plus 10, 0, undefined, right? Undefined. Yeah, but now we have a technique to overcome this situation, right? This undefined situation. That technique is called factor and simplify, right? And simplify. So if we factor this, following difference of squares, the numerator will become the following, right? X minus 5 times x plus 5, right? This is the factorization following difference of squares. Now, on the bottom, on the denominator, I have to figure out two numbers such that the multiplication of the two numbers is 10 and the sum is -7. After some trial and error, you will figure out that those numbers are 5 and 2. But since I want the sum to be -7, this must be negative, this must be negative as well. Now, if you look at the numerator, the denominator, no hard to see that these two guys are exactly the same, right? So we can cancel them. We can cancel them. So we cancel these two. But after canceling, notice we are left with a rational function x plus 5 over x minus 2, right? But what is good is that this rational function compared to this rational function, it's better behaved. Better behaved, Professor, in what sense? In the sense that it will allow you to do the direct evaluation, right? So notice, now I'm not gonna get 0 over 0. Instead, I will get something meaningful. Look, 10 here, 3 here. 10 over 3 in exact form. This is what they have chosen here, right, to show. So this should be choice B, right? Very good, guys. Excellent. Now, probably we should talk about radical forms. Where we did this, you can do this at home. Yeah, this one's at home. Let's try now to talk about these radical forms. Yeah, before the radical form. Yeah, let's I'm gonna show you what to do with this form, right? So before, let's go back to the lecture and let me show you an example here. What if factorization does not help and the expressions contain radicals? What to do? Mathematicians have figured this out, guys. And here is the strategy, the method that you should follow. It requires this definition, the conjugate of a radical expression. What is it? Recall, conjugate of a square root of a minus a square root of b is a square root of a plus a square root of b, right? The first term stays the same. The second term changes its sign. Conjugate of a square root of a plus a square root of b, a square root of a minus the square root of b. Okay, first term the same, second term changes its sign. Conjugate of a minus the square root of b, a plus the square root of b, right? First term stays the same, second term changes its sign. And similarly, the conjugate of a square root of a plus b should be a square root of a minus b, right? All right. In order to make sure that you understand how to take the conjugates, let me give you these 3 exercises here. Anyone could tell us or write on the chat what should be the conjugate of this expression, square root of x minus 2. What should be that? Anyone? Let's see. Quickly. Manur, excellent, right? A square root of x plus 2. Excellent, right? A square root of x, it stays the same, this changes its sign, plus 2. Excellent, excellent. What about the second one? A square root of x plus 1 plus 3. What should be its conjugate? Anybody? Very good, very good. Following the definition of the conjugate. Someone here posted the answer. Manur, excellent, right? Very good, very good. A square root of x plus 1 minus 3, right? Excellent, excellent. The last one, -2 minus the square root of x minus 5. What should be the conjugate of this guy? Anyone? You can write it in the chat or you can say it. Robert, you made my day. Excellent, excellent. Minus 2 plus a square root of x minus 5, right? Yeah. I see you guys are sharp. Negative 2 plus a square root of x minus 5. Excellent, excellent. All right, so we're gonna consider the conjugate for this method. How this method works, I'm gonna explain this method to you via this example number 1, okay? Suppose they ask you to compute the limit as x approaches 5 of this radical expression. Look, a square root of x minus 1 minus 2 over x minus 5. Solution. Well, Professor Retamoso said, always try direct substitution. Well, let's try direct substitution, right? If we try direct substitution, however, notice what's going to happen. This will be a square root of 5 minus 1 minus 2 over 5 minus 5. Unfortunately, this will be a square root of 4 minus 2. This is 5 minus 5, which is 0. A square root of 4, 2 minus 2, 0. 0 over 0, right? Undefined. All right, but the fact that this is undefined doesn't mean that the limit should be undefined, right? Remember, limits are about what happens in the neighborhood of 5, not necessarily right at 5, right? Okay, so then now the strategy is going to be this. Multiply numerator and denominator by the conjugate of this guy. Let me highlight. Why you're taking the numerator, Professor? Because it's there where the radical is, right? Yeah, that's the whole idea. So a square root of x minus 1 minus 2, right? Which is this. A square root of x minus 1 plus 2, right? Plus 2. That's the conjugate. So this is what we're going to do. Mathematicians figure out that multiplying by the conjugate helps to eliminate this undefined situation. You will see. So limit of the square root of x minus 1 minus 2 over x minus 5 as x approaches 5. As x approaches 5, okay? Now, what is that? Well, since we're going to multiply by the conjugate, allow me to do this, right? Parentheses here. We're going to multiply by this guy, right? Square root of x minus 1 plus 2, numerator and denominator, both. So we don't change the value of this fractional form, right? Yeah, numerator and denominator. Now, guys, when you work out this whole limit, let's start on the numerator, right? What's going to happen here? This times this is going to be a square root of x minus 1 is squared, right? It's squared, right? This time itself. Then next, plus twice a square root of x is minus 1 times 2 minus 2 is square root of x minus 1 minus 2 plus 2 minus 4, right? Minus 4. This is the numerator. For the denominator, however, do not expand. Do not expand. I will write a note for you to remember that. Denominator will stay in factor form. I will explain why. So let's write this note here. Do not expand. Note. Let's just keep it in factor form. Keep the denominator in factor form. In factor form. Leave it alone, right? The one that you work out is the numerator. Now, notice that when you multiply a quantity by its conjugate, the following always happens. The second term gets canceled with the third term. They end up being opposites of each other. So this is the whole idea of multiplying by the conjugate. You get to eliminate this part. Now notice that the exponent 2 will eliminate the radical part, because remember the square function is the inverse function of the square root function. So apply one after the other, they undo each other, right? So this will be just x minus 1. X minus 1. The second term, that third term, they cancel. And here minus 4, right? Minus 4. Now, the reason why we keep the denominator in factor form is going to be shown next. Look, minus 1 minus 4 is, algebraically speaking, just minus 5, right? So this is x minus 5, right? And notice that this x minus 5 also appears here on the bottom, on the denominator, right? And that is the reason why you shouldn't distribute this, because if you distribute it, you're gonna miss the fact that these two guys are the same. Okay, so only you work the numerator, the denominator stays the same. So these guys are the same, right? And therefore we can simplify, right? We can simplify that. Now, after you simplify this, you are going to end up with a new function that's going to look like this. Remember what happens when you eliminate this and this? Apparently nothing is left, but remember there is always this invisible one here. That invisible one stays, right? 1. I am canceling these 2, so this guy stays as a square root of x minus 1 plus 2, right? Plus 2. I got a new function that should be better behaved than this original function, right? The original function, look here. Better behave, Professor? What do you mean? Well, I mean, you can now do the direct evaluation without trouble. You will see. If we do the direct evaluation now, 1 over the square root of 5 minus 1 plus 2. 5 minus 1 is just 4. Square root of 4 here plus 2. The square root of 4 is 2. So we end up with this 1 over 2 plus 2. And that is just 1 over 4, right? Final answer, looking exact form. 1 over 4, a quarter, right? 1 over 4. So now it's time for you to practice on number 6. Try to do this question, okay, with the radicals. Follow the example that I gave you, multiply by the conjugate, and follow this, okay? Yeah, so limit, try to do this, 1 plus x minus 1 over x, right? And let's write this as a hint. If you try to do a direct evaluation, right? Nothing wrong with that, right? You can always try that first. This unfortunately leads to a square root of 1 plus 0, 1, 1 minus 1, 0 over 0. So it means that we have to multiply by the conjugate, right? Multiply numerator and denominator by the conjugate. By the conjugate. I'm going to put this between parentheses because it's the conjugate of this guy, right? The conjugate of this. Yeah, by that conjugate. Yeah, multiply top and the bottom, do the algebra. Remember to keep the denominator in this case, right? In factor form, so you don't miss the cancellation. And then you cancel, and then you substitute, right? See if you can figure this out. and try to output your final answer in exact form, right? It turns out mathematicians like a lot of exact form, but I show you, right, that if you use the calculator, if the calculator is giving you decimal form, in our decimal calculator, there's a way to go back and forth from decimal form to exact form, right? I showed.
I got D, Professor, 1/2.
Manur, D, let me see. Excellent, excellent. Manur, you made my day. Excellent, excellent, excellent. Very good, very good.
Professor, you could call me Ma.
Ma. Okay, Ma.
Yes.
Okay, Ma. Excellent, Ma. It has so much value to practice. You don't have to be right all the time, but practice, because in the end, this is what we left, right? When you practice, you get to know. And if there are issues, we will solve the issues, right? Whatever, if something doesn't make sense, we will make sure that it makes sense. All right, great. So multiplying by the conjugate, both numerator and denominator, then we gotta do this, right? Conjugate of this expression is square root of 1 plus x plus 1. And here also square root of 1 plus x plus 1. And now we have to do this algebra, right? That you learned in previous courses. How you multiply this? Well, you kind of FOIL this out, right? This multiplication will lead to the following. Square root of 1 plus x squared. This multiplication, this times this, will lead to a square root of 1 plus x. Now, time to multiply this guy over, this times this, minus the square root of 1 plus x, and -1 times +1 minus 1, right? So we expanded the numerator. With the denominator, you don't have to expand. Indeed, the hint is to keep this in factor form, right? There is a reason behind this, so keep this in factor form. Now, on the numerator, simplifying, we're gonna get the following. Notice these two takes care of this radical, right? A radical square returns just the radical, this 1 plus x, right? Very good. But now the second term and the third term, when you multiply a quantity by its conjugate, they cancel each other. Look, 0 here, right? 0. So this stays with -1. And the denominator, remember, it stays in factor form. Now, Professor, why you kept the denominator in factor form? Well, because of this. Look, 1 minus 1 is 0. So then notice that this x will appear on the numerator, right? And if you keep this in factor form, you will notice that this x is also here, right? That's the reason. Now, turns out that function that they gave us was this one in disguise, right? This one in disguise. So once you simplify this, right, you remove this x from here, you end up with a new function, which is this 1 over, notice I'm removing this 2, the invisible one stays there, right? 1 over 1 plus x plus 1. And you are taking the limit as x approaches 0, right? Now you may say, Professor, you multiply by the conjugate, you got another function, but it still looks complicated. But compared to this is better behaved in the following sense. This will allow me to do the direct evaluation, right? And solve this once and for all. So this will be 1 over the square root of 1 plus 0 plus 1. But 1 plus 0 is 1, the square root of 1 is 1. 1 plus 1, 2, right? 2. So this will end up being 1/2, and that's it, right? That's it, 1/2. That's it. This is it. Excellent, excellent, guys. This one, do it at home, is similar, right? Follow this same method, right? And try to output your final answer in exact form, because otherwise you may not see it, right? There are radicals there. So exact form, keep it in exact form. You should get it. Okay, so now let's move to this other form that you should be aware of. Doesn't have a specific method, but try it out. This is 7 plus h squared minus 49 over h. And they are trying to compute the limit as h approaches 0. Hint, I'm going to give you a hint. Expand the numerator, and simplify. Okay. And you may say, Professor, what if we just plug the value into? Unfortunately, if you plug the value into, which is nothing wrong with doing that, right? You're going to get this annoying 0 over 0 loop. 7 plus 0, 7. 7 squared, 49. 49 minus 49, 0 over 0, right? So because of that, we have to do something else. So expand this guy, FOIL it out, right? And then simplify and try to see if with that we can overcome this undefined situation, okay? Simplify and then plug it into again. The h equals 0. Let's try guys. Then we will move on to trigonometric expression. I see. Very good, excellent. Yeah, very good. Yeah, very good, excellent. Try guys, give it a shot. It's just algebra, right? It's just algebra simplification. Very good, excellent. Excellent. Yeah, deep also, very good. Excellent, guys, very good. And this form, believe it or not, guys, it's important because when we deal with derivatives, we're going to use that form. It's called difference quotient, right? Difference quotient. So we're kind of preparing the ground for that. Okay, so let's do it together, right? If we expand this carefully using algebra, right? So 7 plus h squared is 7 plus h times 7 plus h, right? Unfortunately, I cannot just distribute this. Doesn't work for sums, right? You gotta do this work. So that will be equal to what? Limit as h approaches 0. More students are trying. Yeah, it's good. Try, guys. Yeah. Yeah, Karen. Very good. Yeah, let's see. 7 times 7 is 49. 7 times h is 7h, right? H times 7 is the same as 7 times h. Remember, for product, the order of the factors does not change the product, right? Called community property, right? H times h here, h squared, right? Minus 49, right? 49. Denominator is just h, nothing to do, right? Nothing to do. So now carefully simplify this. Limit as h approaches 0 of what? 49. 7h plus 7h, 14h, right? I just combine these two like terms, right? Plus h squared minus 49 over h. But notice this 49 minus this 49, 0, right? 0. So we end up with this. Limit as h approaches 0, 14h plus h squared over h. At this point, guys, either you factor out h and simplify, or you can simply just divide h into these two terms. Either way, you will end up with the following. Limit as h approaches 0 of 14h over h plus h squared over h. I'm doing this slowly, guys, because you're gonna do something similar in your homework. You will see. Look, h cancels with h, so we end up with limit as h approaches 0 of 14 plus h into h squared is just h, right? It's just h. Turns out this complicated function was just this linear function in disguise, 14 plus h, right? And this is, of course, better behave because it allows me to do the direct evaluation. 14 plus 0, and this guy ends up being just 14. Excellent, excellent, guys. So this, right? Very good, very good. Yeah, try to remember this for your homework. You're gonna need it. All right, so moving on. Now we have to talk about trigonometric expressions, right? Trigonometric expressions. So what if direct substitution doesn't work? I will talk about this. Now let's talk about this trigonometric expressions. Yeah, special limits, I call it. Recall first that we showed before that the limit of this expression, sine of x over x, as x approaches 0, was equal to something. Anybody remembers what this limit is equal to? Remember, we created a table, and then we work out with that table, and we got to some conclusion there. But what's that limit? Anybody remembers? And as a hint, I'm going to give you the graph of this function, okay? Maybe from there you can catch it. Let me see the graph. Let's graph the function sine of x over x. Y equal sine of x over x. Look at this, guys. Let's make it bigger. Try to see the behavior of the function as you approach from the left and from the right to this point. Look, it's undefined there, right? But looking at where is it headed from the left and from the right, even though it's undefined, here is a hole there, right? I see some students kind of remember. Yeah. It's 1. Yeah, but we'll, yeah, very good, very good. Yeah, remember in the previous lecture that was live last Wednesday, right? We talk about how using tables we can get this guy done, right? Using tables, approximating from the left and approximating from the right. If you use a table, it is possible to see that the values of this guy, they approach to 1 from the left and 1 from the right. Another way is to use our Desmos graphing tool and see that this function when graph shows this, right? There is a 1 there. So when you approach from the left to 0, the output values are headed to 1. When you approach from the right to 0, the output values are also headed to 1. Now, right at 0, look, notice that this function is undefined, right at 0. But on the neighborhood, the output values, when you approach 0 from the left, they are headed to 1. When you approach 0 from the right, they are also headed to 1. So this should be 1, okay? 1. So let's try to remember that, to memorize that, so that we can use it for computing more complications. So this from now on should be equal to 1 as a property, right? As a property. But now, what if they ask you to compute the limit of sine of k times x over kx, where k is some real number not equal to 0? Could be 3, could be 4, could be 2. Let's explore what happens if we consider here a constant. Okay, right? Let's see if the limit changes, right? Let's see. So again, let me use our Desmos graphing calculator and let's explore that, right? I encourage you guys to play around with this tool because it will help you to understand all the facts that we're gonna get and also to verify your knowledge, right? To check. Let's see. I want k to be, let's say, suppose k is 4. 4x over x, over x. Look at the graph. Look at the graph again. And this is 4x, right? Forget the 4 down here. Look at the graph. Even though we change this for number 4, the graph is still look, as we approach 0 from the left, the output values are headed to 1. As we approach 0 from the right, the output values are still headed to 1, right? You see it, guys? At 0 is undefined, but in the neighborhood of 0, the output values are headed to 1 from the left and from the right. So this is telling me that this should be still equal to 1, right? This limit is still equal to 1. So as long as the constant is here and here, the same constants, this should be still 1. Now, if you don't believe that, look, change this 4 for a 5 or for, let's say, a 6, and you will see the same. Look, still 1 here, right? No matter what constant you write there, positive or negative, you will get this guy there, the 1. 1, always, okay? So this is a property mathematicians discover. So besides this, which we're gonna call property 1, this is property 2. This limit is also equal to 1, always, okay? Yeah, very good. So this is gonna be called property 1. And this is going to be called property 2. This is also equal to 1. All right, so examples or applications of this. Suppose they ask you to compute this limit. Compute the limit of sine of 8x over 8x. Following property 2, anyone could tell me what should be this limit equal to? Very good, guys. Yeah, good. The students figuring this out, right? Notice that since this property is true for any value of k, in particular for k equal 8, right? We can apply the property, right? Excellent, right? Deep also. Yeah, very good. Yeah, so this guy is just application of property 2 for k equal 8, right? K equal 8. So as an application for k equal 8, using property 2, then the limit of sine of 8 times x over 8x as x approaches 0 should be just equal to 1. Again, right? 1. As long as these two guys are the same, this and this, as long as they match, this should be 1. Okay, property 2. Very good, guys. Now I'm gonna give you another example where we have to do some tricks. I'm gonna do it very slowly. You will have to do it in your homework. It will help you. So try to catch this. Suppose they ask you to compute the limit of sine of 9x over x as x approaches 0. Let's try this. Yeah, and then we will practice on the worksheet that I have there. Limit as x approaches 0 of the sine of 9 times x over x, okay? What should be this equal to? Well, notice that if I kind of follow some wishful thinking, right? I wish I had a 9 here. If I had a 9 here, this result will be 1, right? There is no 9 here, but we can make it appear by multiplying numerator and denominator by 9, right? By 9. I see Miguel figured this out. Deep figured this out. Excellent, guys. Excellent, right? Yeah, excellent. So when you see this, when something is missing, follow this so-called wishful thinking technique, right? and imagine that what is missing here is there. There is a 9 there, right? But in order to keep the value of this fraction the same, if you introduce a 9 that is not there, right? It's not there, the 9, but you put it there, then you have to multiply by 9 also the top, so that these two cancel and you are still dealing with the same expression, right? You follow, guys? When the 9 or the constant is not there, multiply it by that constant top and bottom, top and bottom. So then it will appear there, right? Now, separate this 9 from this part, right? Using this so-called constant multiple rule, right? Take this outside of the limit, right? And then you will end up with this, right? Sine of 9x over x, right? But this is just the following: 9 here, this guy, nine, don't forget the 9 there. Let's write it in blue. This guy, this 9, sine of 9x over 9x, when you take the limit as x approaches 0, this guy has a value. It's just 1 following property 2, right? By property 2. Right? So therefore, final answer, this is equal to 9. Excellent. Right? The limit is equal to 9. Yeah, so, and you may say sometimes, you say, but Professor, what if we just plug this into there? Yeah, this is something that you can always do, guys. There's nothing wrong with that, right? But notice that it wouldn't work, right? It wouldn't work. Sine of 0 over 0, this will be 0 over 0, right? So because of this undefined situation, we use these tricks in order to overcome this, right? Remember, multiply by 9 top and the bottom, take the 9 out, and this is 9 times 1 equal to 9. Yeah, following this trick, probably we can do some, and then I will show you some other situations there where we need to apply more tricks. Yeah, so let me see if there is something. Yeah, let's do this example 3, and then we'll ask you to do something on the worksheet. I saw it already. Suppose you have this situation, example 3. Compute the limit as theta approaches 0 of the sine of 7 theta over 3 theta. All right, we just dealt with this form, right? Sine of something times x divided by x, right? We just did that. Look, sine of 9x over x. So let's try to separate this part from the number 3, because we know what to do with this part, right? We're going to apply that technique. So carefully do this. Limit as theta approaches 0 of 1/3 times sine of 7 theta over theta. Professor, why you are breaking this down this way? Because I know what to do with this form, right? We just did it before. All right, next, I'm going to take this constant out, 1/3. Then here, limit of sine of 7 theta over theta here as theta approaches 0. As theta approaches 0, right? All right, great. So now I know what to do with this guy, right? We just did it. Wishful thinking strategies suggest I don't have the 7 here to claim that this limit is equal to 1, right? If you don't have it there, not a problem. Just put it there. Introduce this number 7 there by doing the following. Sine of 7 theta. There is no 7 here. I'm going to write here 7. but that comes with a price. Immediately I have to multiply the numerator as well by 7, right? So that will be just this. So when you multiply by a constant the denominator, you have to multiply by the constant numerator as well to keep this value the same, right? So put 7 here, put 7 on the top. But now it's time to take this out, right? Take this out. So you will get this 1/3 times 7 outside, right? Limit as theta approaches 0 of sine of 7 theta over theta, right? Over theta. But don't forget the 7 there. Aha. But the good news is that I know the result of this limit, right? I know. Yeah, anybody could tell me what is the result of this piece, this part, based on property 2? By property 2. Very good. They're writing it in the chat. Very good, guys. Excellent, right? It's just 1, right? As long as this guy and this guy are the same, remember we graph this function, it shows that the limit of this part is 1, right? 1. So 1 times 7 times 1/3 should give me the final answer, right? So 1 times 7 times 1, 7. 3 times 1 times 1, 3. 7/3 in exact form, right? Is the answer, the final answer. Yeah, very good, guys. So this is how you proceed, right? Right now, we don't have more tools, but in the future, when we reach the final part, the third part, there is this rules called Hospital rule. This will simplify this a little bit, but at this point, we have to follow this trick, right? Because we don't have more tools yet. We don't know about the derivative yet, right? Great. So now with this background, we're going to go over a lot of different forms. I want you to be aware of all these forms so you will be okay with your homework. So, and we will clear things up. First, before you start, let me start with this form. It's going to be tricky. I will show you this. I will ask you to number 2, okay? Let me try this form. Suppose they ask us to compute the limit as x approaches 0 of 5x minus 3 sine of x over x. How can I deal with this? Well, I know that sine of x over x, the limit of that when x approaches 0 is 1, right? So somehow I should try to put this x together with this sine of x, right? And then this can divide this other term this way. Isn't it true that this is just equal to this, the limit of 5x over x minus 3 sine x over x, right? Distribute the division by x, right? This cancels. X with x, they cancel, and they give me just this, limit of 5 minus limit of 3 sine of x over x. This looks better now. Why you say that, Professor, that it looks better? Well, because now I can say that this is equal to what? Limit of a constant function that I know how to handle, right? Limit of a constant function, approaches 0, minus the limit of this function, 3 times sine of x over x. I have this constant number 3. I can take that constant outside of the limit and focus on figuring out this limit, right? Now, limit of 5, constant function 5 as x approaches 0. Anybody could tell me what's this limit? Yeah, very good. Limit of constant function. Remember this constant function. Excellent. The constant function does not change. Even when you take the limit, does not change. It stays the same. It's 5. Very good. Done this part. 3 times what? What is this part? This, anybody? The limit of sine of x over x. Hint, follow property 1. By property 1, what is this? The limit of sine of x over x. Anybody in the chat, please? Mhm. Yeah, very good, guys. So limit of sine of x over x. Yeah, very good, Mark. It's just 1, right? Just 1. So now multiply 3 times 1, 3. Take that away from 5. This should be just 2, right? You follow that? 2. Very good, very good. And you may say, Professor, wouldn't it be enough just to plug this into here? Unfortunately, guys, when you plug this into, you're going to get 0 over 0, right? That is why we did all that. But always you can try this. If it works, then you're done. But if it doesn't work, don't panic. Just sine of 0, 0, this 0 over 0. Just apply some tricks that I'm giving you here, right? And overcome this situation, right? And then it's 2. Don't go for this. That's not, it's a meaningful number, is 2. Try to do exercise number 2, guys. I will leave this as a reference, okay, for you to follow. So try to do this now. I'm gonna write it bigger here. Limit as x approaches 0 of minus 7x minus 8 sine of x, all that divided by x. And the hint, as usual, is this. Divide x into each of these two, break it down, right, as I did there, and try to see if you can figure out the answer, right? Very good, very good. I see students are posting answers, which is good, right? Try, guys. You don't have to be right all the time, right? What is important is to try. Deep. Very good, deep, very good. Yeah. Yeah, excellent, excellent. Very good. Excellent, excellent. Very good. You figure this out. And try to kind of come up with patterns, organize your knowledge, you know. This exercise, these forms, they show patterns, so follow them, right? And again, guys, since we don't have sophisticated tools yet, this is the only way to go over this exercise for now. But in the end, as we gather more and more knowledge, you will see that there are some alternatives that I will show you later. Okay, so let's see. Take a look at this together. You break it down, right? As follows. Limit as x approaches 0 of minus 7x over x minus 8, limit here, distribute your limit. Minus limit 8 sine of x over x, right? Great. And this is as x approaches 0. Here, after you cancel these two, right? This x with this x, you end up with the limit of the constant function -7 as x approaches 0, right? Minus the limit of this sine x over x with 8 multiplying outside. Look here, I have applied the constant multiple rule, took this 8 outside, I focus on taking this limit, right? But now, this is the limit of a constant function. The constant function equal to -7. The limit of a constant function is equal to this constant value, right? Great. Over here, we have 8 times this well-known result by property 1. By property 1, this is just the number 1, right? The rest is just algebra, right? Or arithmetic, if you prefer. Algebra, I would say. -7 minus 8 times 1 minus 8, -7 minus 8, minus 15, right? Minus 15. That's it. Excellent, excellent. Great. All right, so that was one form. Let's check other forms. Let's see if we can try this now. Yeah, this one I gave you a background. Let's see if you can remember what to do. Try this, guys, now. limit of 9 times sine of x over 3x as x approaches 0. Hint, separate this part, right? Separate this from the rest. Separate this, take this constant part out, and you shouldn't have a problem figuring this out. Yeah, go ahead, try. Let's see. Yes, similar questions will come out on your examination, so try to get used to these forms, guys. They're very, very basic forms, but useful. So master them. Oh, there's no tangent there. Let me check that out. Yeah, I'm always try, guys. Try. Mathematics is often mastered by practicing, right? So yeah, it's okay, Robert. It's okay. Yeah, you can just watch the rest of the lecture where it's recorded in case you have to take another class. You have to go.
Okay,
yeah, very good.
You have a good
yeah, very good, Robert. Yeah, great. Yes, thank you for coming. Yes, yeah, the rest you can watch it. It's being recorded. Great, excellent. Yeah, okay, guys. Great. Yeah, so any answer for this question number 3? Try. Yeah, and then we will deal with tangent and the cube ones, the cubic forms. And when you're dealing with your homework, go back here, check, or ask me, right, for hints. I can always give you hints. Yeah, recall property 1 says that the limit of this guy is just 1, right? It's just 1. All right, let's do it together then, right? If you take this out, 9 over 3 is just a constant, right? It's a constant out. Then we are left with the limit of sine of x. Someone figure this out. As x approaches 0, right? Sine of x over x as x approaches 0. Yeah, excellent. Good. Excellent, right? So now we know that 9 over 3 is just 3, and the limit of sine of x over x as x approaches 0 by property 1, right? Property 1 is just 1. And 1 multiplied by 3 is just 3, right? It's just 3. So that's it. This is the final answer. This is it. Yeah, this guy is similar, right? So I leave this for you to do at home. Let's try to figure this out now. This one. Can you figure this out? It's a little bit tricky, but I will give you the hint, okay? First, try to separate the constant part from this part. Okay, so that this will come out, right? This will come out. 10 over 8 multiplied by the limit as x approaches 0 of x over sine of x. Professor, I know this limit, the result of this limit as x approaches 0 of sine of x over x is 1, right? But here is kind of flipped. How can I use this to get this? Well, guys, remember that this guy in algebra, x over sine of x, so I recall 1 over x over sine of x is just sine of x over x, right? When you divide by a fraction, you flip this fraction and you multiply, you get this. So this is saying or telling us that this can be rewritten as follows. The limit as x approaches 0 of 1 over sine of x over x. It's very nice and clear here. Sine of x over x. Okay, 1 over, right? This gives you this. But then in turn, this is saying that this should be 10 over 8, 1 over the limit of this constant function y is just 1, right? Over the limit of sine of x over x, right? As x approaches 0. But basically at that point, we are done because this is 10 over 8, 1 over what? The limit of sine of x over x as x approaches 0 is just 1, right? 1. 10 times 1 is 10. 8 times 1 is 8. Simplify. Mathematicians appreciate it if you simplify, divide both numerator and denominator by 2. This will be 5 over 4. Right? 5 over 4. Look for your answer. Is there. Excellent, right? Yeah, number 5. What's that? Mm-hmm. Yeah, so basically, if you are dealing with this limit, x over sine of x as x approaches 0, that is also equal to 1. This is what this is saying, right? So property 3, then maybe we should, you're gonna need this, all these properties for your homework. Property 3, let's say that this guy, yeah. Let's write here, right? Property 3, the limit of x over sine of x as x approaches 0 is also 1. Is also 1, right? 3 properties for you to use, guys, when you take your examination, when you do your homework. Okay, good. Now, using that property 3, can you try this? Hint, use property 3. You know, when we have good tools, easier, right? Easier. Now deep, figure this out immediately, basically, right? Yeah, we're saying that property 3 says that limit of x over sine of x as x approaches 0 is also 1. It's also 1, right? So when you look at this exercise, then you can say that the limit as x approaches 0 of 7x over sine of x, this is 6, right? Once you separate this part, x over sine of x, from the constant that we're going to pull out, then basically this tells me that this is just equal to 7 over 6 times the limit of x over sine of x as x approaches 0, right? But we just said that property 3 says that this guy is still 1, right? 7 over 6 times 1 equals 7 over 6. And this is it, the limiting exact form. Excellent, excellent. Very good, guys. This one, right? Very good, Professor. Now, what to do if we have tangent there, tangent? It shouldn't be a problem, guys, because I know you did well in pre-calculus, so you should remember this. A tangent in pre-calculus, they show you that is equal to sine of x over cosine of x, right? I try to catch this, guys. I think this you will need on your homework. Tangent of x is always equal to sine of x over cosine of x. It's called the quotient identity, or one of the quotient identities. Tangent sine of x over cosine of x, and cotangent is cosine of x over sine of x, right? So we're going to use this here. So this tangent that you see here, we're going to rewrite this as sine over cosine. Sine of x over cosine of x. Now, let's simplify this. This is going to be equal to the limit as x approaches 0 of what? Remember, when you divide here, let's write one below here, below the x, you flip the fraction here on the denominator and you multiply, right? So this will be equal to the following: 3 over 5 multiplied by sine of x over cosine of x times the reciprocal of this, 1 over x, right? 1 over x. Yeah. But now, what is this equal to? Well, after taking this constant out, right, we have a property, the constant multiplication rule, right? This will be just this, right? Limit of sine of x over x. Allow me to put this together. Part is this times 1 over cosine of x. Professor, why you are doing this? Well, I'm trying to group the stuff, the form that I am comfortable with, right? Which is this, right? And this part, 1 over cosine, I am putting this here separately, right? This multiplication is the same as this. I'm just rewriting this in this form so that I can compute my limit. So then simply do this, 3 over 5 limit of sine of x over x, which is something that we know what is this equal to, right? Times the limit as x approaches 0, 1 over cosine of x. This limit is just equal to 1, right? This other limit, I don't have a formula, but turns out is well behaved, this expression. Why you say that, Professor? Well, because if you substitute the 0 directly there via a direct evaluation, you get this, right? Now, cosine of 0 is just equal to 1. 1, isn't it 0? Turns out it's 1. I will show you. If you forget the fact that cosine of 0 is 1, you can always calculate it in your Desmo scientific calculator or any scientific calculator. Cosine of 0, 1, right? To play safe, always make sure that you're working in radians, right? 1. Cosine of 0, 1. So then, therefore, this whole thing comes down to 3/5, right? 3/5. There you go. And this is what you have to choose as your answer. Let's finish with this number 8. I'm going to do number 8 and I'm going to let you do number 9, okay? Let's say you have cubes here, cube sine of x cubed over x cubed, and you are taking the limit as x approaches 0 of the sine cube of x over x cubed. What to do? Well, try this, guys. Try this. Try to rewrite this as follows. Limit of sine of x over x cubed as x approaches 0. Why you are writing this as a cube, Professor? Well, because I have this power rule, right? Power law that says that I can introduce the limit inside a power, right? So this should be equal to limit of sine of x over x as x approaches 0, all cube, right? You put this limit inside the cubic function, right? Very good. But this limit, we know what this is, right? It's just 1, right? 1 cube, 1. Very good, guys. Number 8. Number 9, try it and see if you can figure this out on your own, okay? Let me just put this back and then we will finish with that. Yeah, very good, very good. Let me rewrite it again. So sine of x over x, right? Approaches 0 cubed. And then we put this limit inside the cubic function, we said, right? So limit sine of x over x as x approaches 0, all cube. This limit by property 1, is just 1. 1 cube is just 1. Final answer, right? This is it. That was for number 8. For number 9, try to apply some tricks here. sine square of x over twice x. As x approaches 0, try to figure this out. First hint, I will give you this hint. Separate the 1/2, the constant part, from the rest. Separate this, take this 1/2 outside, and then break it down. Maybe you can write sine of x times sine of x, right? And then it should come out there. Try to figure this out. Someone figured this out already. Yeah, very good, guys, very good. The more you practice on this strategy, I know it's annoying at this point, but later on, when we look at derivatives, I will give you some alternatives in case this is not the strategy of your choice. Deep figure this out. Yeah, Deep, but think about this, right? There is an extra sign there. So consider the sign, right? So let's do this. Let's check this out. Yeah, you're close, but notice this guy is not sine of x over x. It's sine square of x, right? So because of that, I would suggest do this, right? Times sine of x. Break it down this way. Yeah. I try to see, and then distribute your limits. And try to figure out the answer. It was close what you said, but it's a little adjustment there. Yeah, so distribute the limit, and then I think that will be it. Okay, guys, so let's do it together, right? So we can finish this up. If I distribute the limit, I will get this, right? Limit of sine of x over x as x approaches 0 times limit of sine of x as x approaches 0, right? Now, this will be 1/2, right? What is this limit? Anybody could tell me what is this limit? Limit of sine of x over x as x approaches 0? My property 1, that should be just yeah, it's a tricky business, I understand, guys. Yeah, 1. Very good, Karen. Very good, Mom. 1, right? 1. This is 1. And anyone could tell me what is this one, the other one? Look, the limit of the sine function, sine of x, as x approaches 0. Hint, just plug the value into. Plug the value into. Ma, you made my day. Yeah, my saying 0, right? Excellent, right? Excellent, because if you plug this value into, it turns out the sine function is well behaved. The sine of 0 is just 0. Professor, you didn't say 1. That was cosine of 0, right? Let's recall, guys. Let's clarify our knowledge. Cosine of 0 is 1, but sine of 0 is 0, right? Yeah, these are facts from previous courses that we need to have very clear, right? Yeah, cosine of 0, 1, sine of 0, 0. Very good. So because of this guy being 0, the whole multiplication turns out to be 0, right? 0 times 1, 0 times 1 has 0. So believe it or not, guys, this whole thing comes down to 0. And this is what you have to choose, right? Excellent. Okay, guys, I think it's enough for today.